Hi, in this video I would like to show you how to add radial reinforcement to a Revit project by using Dynamo. The project we are going to work on consists of a circular shaped floor with an opening in the middle. Specific on this floor is that the thickness is varying towards the middle of the circle. We are going to create two parts of the reinforcement. We will have the bottom part, which is a flat reinforcement consisting of two layers, and we will have the top part of the reinforcement, which will be along the varying slope of this floor. The workflow we need to follow for this particular project consists of these four parts. The first part is that, of course, you need to create your geometry in Revit. In the second part, we are going to take the surface, a specific surface of that geometry, back into Dynamo using some specific nodes, and we are going to use that surface in a third step to create the rebar center lines. These rebar center lines will form the basics of the rebar objects in Revit, which will be created by the Dynamo for Rebar package. Before you start modeling, it's very important that you set out the parameters you want to use for it. Now in this case, the cover is very important. We need to have a cover, in this case, of 40 mm between the bottom surface and the bar, the rebar object. Now, as we are going to use rebar center lines, it is important to recalculate those distances for the cover with, for instance, the cover to center of the first layer, which is indicated by C1, and the cover to the center of the second layer, which is indicated by C2. Let's have a look at the real project. Now, this is the floor which has been modeled already in Revit. And as you can see, the floor has a varying thickness, which has been created by using the Modify Sub-Elements tool. Let's open a more wireframe view of this floor so we can see afterwards the rebar being modeled by using Dynamo. So we are going to open Dynamo 0.9 for this case. And we are going to start with the bottom reinforcement, which is just a flat reinforcement, so no slopes indicated for that. As you can see, the script consists of a few parts. Now the green parts consist of input elements like geometry and parameters. And then we will discretize some specific elements, let's call it the reference elements from that surface, create the center lines from it, create the radial and the tangential reinforcement objects in Revit, and then optionally you can also set representation of these rebars. Let's start with the first thing, which is the geometry input. So therefore I need to minimize a little bit this screen so I can easily pick the geometry from Revit. Now we are going to need the face, and I need for that the bottom face. There goes. And secondary, I also will select the whole model element. This will be used later on when we are going to create a rebar by means of the element.id. Therefore, we need to have it indicated as a host object for the rebar, which I will explain in a few seconds. The rebar properties, it would be a better view if we maximize the whole screen again. The rebar properties are detecting the rebar bar type, which are preloaded already into our Revit project. Now in this case, I need to have a diameter 18. So the diameter 18 rebar bar type object has some specific parameters, whereas bar diameter and the standard hook bend diameter. Now we can detect the values from these two parameters, which can be used further on in the code block for making the specific calculations for the cover settings. Now these values come in as feet. Therefore we need to convert them into millimeters, as my project is a metric project expressed into millimeters. So what we are going to do in here is discretize the reference elements. Why do we need that? Well, if we take the surface from the Revit object straight into Dynamo, then sometimes it could happen that my isolines, which I will need for the radial reinforcement, are not calculated in the way I want to have them. So therefore we are going to recreate the surface as a native Dynamo object. And the easiest part to do that is by detecting the perimeter curves from the surface I got in, and then make a new surface by using the surface by loft, and then there on that we can create the getIsoline function. So let's start with running the script for the first time. There it goes. As we can see, we get the surface of the bottom part of our floor. We get two perimeter curves. The first one is the outer perimeter curve. The second one is the inner curve. And also we were going to get the surface point at parameter at 0.5, so this one will indicate a center point. There it goes. This is the center point. These are the perimeter curves. And finally, this is the isoline. Now this isoline will be the basis of the whole radial reinforcement. Now as we can see, the center line, or at least this isoline, is connecting the two circles. So this rebar, if this would be a real rebar in Revit, then it would touch the surface edges, which is not possible of course, because we need to set a cover. Now to do that, to make it shorter, there is a node coming from the Dynamo for rebar package, which is called rebar.shorten. If we go into the catalog, we can see Dynamo rebar, then again Dynamo rebar, and there we have the shorten function. Now the way this node is working is it needs to have a curve as an input, and the length is the shortening length we want to apply on that curve at both sides. So in this case, if we follow this line, you will see that it will be connected with the cover parameter. So in this case, we are going to shorten the curve with 40 millimeter at both sides. If we hide all of these and then show this line, then you will get this as a result, a shorter line. Secondly, it's very important, of course, to set your offset for the vertical position of that rebar, or at least from the rebar center line. So we are going to translate this line vertically according to the z-axis with a distance which is equal to the cover to center first layer. And this gives us this result. Let's zoom in a little bit. There you can see a second line above the shortened line. So this one is not necessary anymore, or at least the preview is not necessary anymore. And then finally, we need to copy this line along the circle, so we need to make a polar array from these lines, which is done by the geometry.rotate function, which gives us this result. The second part is a tangential reinforcement. This will be the circular shaped reinforcement lines along these radial lines. Now to do that, it's very important to have a reference for that circle. And we had the perimeter curves from this part. As you can see in here, these are the perimeter curves, but these are of course too long. We don't want to have a full circle rebar, we want to have segments. And to get those segments, we need to trim that parameter, or at least we need to trim that curve using parameters. So there is a start and an end parameter for that. The start parameter will be 0 degrees, and the end parameter will be a calculated value which is equal to the sweep angle plus overlap. So that overlap will indicate afterwards, or lap splice length, to have the several tangential reinforcement lines. Now the sweep angle in this case is 22.5 degrees. So we want to have a radial, or at least a circular element which has a length of 22.5 degrees plus 1 degree for the overlap. And this will result in this kind of curve. Now we need to hide the perimeter curves of course as well. So this is an element which is consisting of an angle between 0 degrees and 22.5 plus 1, which is 23.5, of course. Again, we need to apply an offset, a vertical offset for the second layer in this case, so it needs to have a higher distance in accordance to the bottom face of the floor. And we also need to offset them towards the middle of the circle, which gives us this result. Now also on this part we need to create a polar array again. Now this gives us this result for the even partitions and this one for the odd partitions. Now the reason why we are splitting up the partitions is because we need to have an overlap. You cannot have all these lines at the same radius of the circle, otherwise we would have a clash of our reinforcements. So the odd partitions will be moved a little bit. So there will be an offset applied on that, which is equal to the diameter of the bar. So if you hide these ones and then open these lines, there it goes. Then you can see, if we zoom in a little bit, that we have an overlap between the two consecutive tangential reinforcement lines. And at the end we will also apply some specific nodes to handle the lists. So we are going to regroup the list that way that they are grouped into a container. So each container will have 8 curves, and this will be used later on when we are going to create the rebar sets. This is the final result of the rebar center lines. Okay, the last step is to create the rebar objects in Revit. Now to do that, there are some specific nodes in the Dynamo rebar package. The first one is let's open the right catalog, is the rebar by curve, and this node will create all kinds of single rebar objects. So each curve will be represented as a single rebar in our Revit model. Now this could give us some issues when you want to annotate. I don't want to number each rebar as a single item. I want to have them grouped in some kind of rebar sets. And therefore there is an option called rebar container. Now this rebar container will group all the same curves, or at least the curves that are grouped in the right way, like I did here in the list.flatten node. So this means that each of these 8 curves will be grouped into one item. So this item will create one rebar container. Now, how is this node going to work in the Revit model? Well, as you can see, there are lots of inputs needed for that. So the curves, these ones are the obvious ones. These are the curves that are created in here. These are the center lines of our reinforcement. So I will take this geometry output and add it to the curves. The second input that we need in here is the host element ID. So Revit needs to know which object will host the rebar, and this is done by using the element ID. So we did that already before in the first step of the script, where we have selected the model element and then extracted the element ID from it. Of course, this is also possible by taking the element ID from this face, but this is not out of the box. So there exists some specific custom nodes that can detect the ID of the face that has been selected. The rebar style, this one will indicate if you are going to use a standard rebar or a stirrup. Now you have to be careful with this one because some types of rebar cannot be created as a stirrup style. So in this case, it's not a stirrup that we are going to use. These are just standard rebar objects. The rebar bar type is connected with our diameter 18. We select it in the first part of the script. And then we have the hook orientations and the hook types. So in this case, I want to have a left hook for either the start and the end, and the hook needs to be 90 degrees. Now it's also very important for Revit to know in which plane the hook should be created. Now in this case, the hook should be created in the vertical plane, or at least perpendicular to the surface of my floor. Now how can we define that plane? Well, that one is done by the last input, which is called vectors. With the vectors, you need to define the normal vector of the plane where the hook should be placed in. So in this case, it's very easy by just taking the line and create a normal vector, for instance, at the start position of that line. So this will mean that each line will have a other vector, which will generate a specific surface, which will be vertical. So the surface will be vertical, and it will be along the length of that line. So in fact, the surface will be the z-axis and the length axis of that line. In that field, in that plane or surface or whatever you call it, there the hook will be created in the Revit model. So for this input, the curve, we take the same geometry as we have put in this field. For the tangential reinforcement, we are going to work at the same way, going to take the input from the tangential lines, connect it with the curves field, and in this case we don't need to have a hook, but still you need to create a curve.normal for that, because afterwards you might want to change the hook position in the Revit model. Finally, these both rebar containers are also connected with a specific node called rebar container.setSolidInView. Now this rebar container setSolidInView node will take all the rebar containers that are added to this list, and it will set the representation to solid in the views that are indicated in here. So by using a list.map function, you can browse through all the views that you have selected in here and add it to the list, and then set the solid state in all of these views. Okay, let's start the creation of the objects in our Revit model. So first I'm going to restore down the view of Dynamo so that we can easily see the result in Revit, and then start running. There we have our results. So as you can see, the hooks are vertical and they are positioned in a surface, in a plane, which is indicated by the length of the bar and the z-axis. You can also easily see the overlap that these two tangential reinforcement objects get. Now, particular for this rebar container, as I told you, is if you select one of these elements, you will see it's a grouped element. So you can get the second line, the third line, and so on. And you can see in the properties that we have 8 bars, which have a length of 4,760 millimeter and has a shape of 67, which is the shape code. This is done for each of these elements in here as the radius is changing towards the middle of that circle. Now, if you are going to have a look at the ones that need to follow the inclined surface, you're going to open for that another script, which is called inclined. And for that, the geometry input is slightly different. The reason for that is the surface of the floor is having a varying thickness, and that surface is not coming in as a native dynamo face, so this will give us some troubles in getting the isolines again. So a workaround for that is by detecting the edges instead. So I'm going to detect the edges of the outer circle, which is this one and this one. Finish the multiple selection and get the edges of the inner circle. Finish. And then we are going to select the model element again, which is this floor. There goes. And we can start running the script. And here we have our perimeter curves. Now these perimeter curves are connected to some specific nodes to join them as one curve, and then we are going to create a new surface. So this surface by loft will generate us that inclined surface that we have in our Revit model. But this one is now a native Dynamo surface, so this one will also be easy to detect the isoline from it, which is given in here. So the same way as we have done for the bottom reinforcement, we need to shorten the rebar length, and we are going to translate it vertically to get it into the first layer, and then rotate it to have it as a radial reinforcement. Now the tangential reinforcement is a little bit different. Why is that? Well, this one is the same. We are going to trim the curve until we have a specific circular curve that has the right length. We are going to offset it towards the middle. We are going to create polar arrays of it and having the offsets for the overlap of the bars. So finally we will have this result. But these elements are created in a flat surface. So they are created in the surface where the first line has been created. So it will be in some plane, well, we can call it the XY plane. Now, in my case, I don't need it in an XY plane. I need to have it in a specific plane which is following the top surface of that floor. Now, what we can do for that is reuse the surface we initially created in Dynamo as a native object, and we can apply an offset to that surface, which looks like this. So this is a surface with a negative offset on it, and this negative offset is equal to the offset for the second layer. Now this forms the center lines, or at least the center surface of the tangential reinforcement for the second layer, and the surface can be used at the end to create a projected curve. So what we are going to do is we are going to take the radial reinforcement, or at least a tangential reinforcement, which is parallel with the XY plane, project it to the surface which has the inclination as the top surface of the floor, and this will finally give us these lines. So we need to switch off these ones. We will have these lines which are follow the slope of the top surface of that floor. Similar as we did with the bottom reinforcement, we need to connect the right lines, or at least the right curves, with the input nodes for the curves and for the normal vectors. We're going to minimize this one a little bit and then run the script. Here we go. Let's have a look at the projected view. There we have our inclined rebars, which are indicated by this orange color. The result at the end could look like this. If you go to a sheet, position everything on the sheet, and then use the specific numbering tools to have the right numbers on it. And then you can start annotating. So as you can see, 8 times diameter 18 with a specific length, and this one is the specific mark for that rebar container.